All right, so we left off, we were going to talk about the Lysozyme case study that's in your book. So this particular case study is really surrounding the mechanism associated with the lysozyme activity, how this enzyme operates, what's particularly going on in this. I hope you read through this. As I had already expressed, I want you to get in groups in just a little bit and discuss this, do some literature search regarding this particular study. So the lysozyme itself is an enzyme that's found in tears, saliva, mucus, things that are exposed to the external environment. You know, I kind of think about animals like licking their wounds. Like, if you think about the lysozyme activity, it is almost like a natural antibiotic, right? So what it does is it cleaves this peptidoglycan layer, which is a peptide substituted polysaccharide, and then that results in lysing the bacteria and cell death. And I often wonder if that was inherently built in, you know, to consider maybe that was something that we did, was maybe we did lick our wounds when we didn't have anything else to treat it with. And maybe that was a way that we were designed to have that activity where we could, you know, not have those types of infections that would occur. It's kind of interesting to think about. We're going to discuss in particular the mechanism associated with that cleavage here on this NAM residue and the particular conformation that's achieved with that particular sugar residue. So here's a little bit more of a detailed picture, just basically showing that within the activated site. NAG is the N-acetylglucosamine residue, and NAM is the N-acetylmuramic acid residue. And you end up with essentially a NAG-NAM trisaccharide that's encased within the lysozyme cleft or the active site. And the next slide actually gives you a better view of that in the three-dimensional conformation. So they've showed you at the front of this where the active site or the cleft is facing you, and then they turn it to the side so that you can get a better view of what that looks like there. The first proposed mechanism was done based upon really seminal results by Phillips and coworkers, and this happened in 1966. This actually was a really groundbreaking type of work or discovery, because Phillips, for the first time ever, did something. What did he do? Or what did his group do? It had never been done before. What did he do? I'll give you a hint. Look at this slide. What if we talked about how those structures are determined today? Say again? Okay, computer programming actually comes later.
Based on its function? Based on its function?
Not based on its function. Always. Come on. The structure itself. The structure itself. So this was the first time someone had actually crystallized the enzyme to study the structure and the function of that particular enzyme, okay? And so this happened back again in 1965, 1966. Phillips actually published this in 1966. I found the publication, the original one. but this was really groundbreaking work that had not been accomplished before, and that's why it was such an important study. So Phillips proposed the left-hand side over here for this mechanistic study, where you have this glutamic acid residue and this aspartate residue, and based upon his thoughts or his hypothesis, there was this half-chair conformation that he proposed as the essential reactive state within the cleft of that particular enzyme. And I've got some questions for you guys to answer, and I want you to get in your groups, and I'll put those questions up here in just a minute. But one of the questions deals with that half-chair conformation. And then there's this oxocarbenium ion that was also proposed. And Phillips proposed that this was an electrostatic type of interaction, even though there were acid-base type reactions and stabilizations happening within this particular mechanism. He proposed that there were electrostatic interactions that stabilized the oxocarbenium intermediate. Now, I will tell you, in organic chemistry, oxocarbenium ions are fairly short-lived. They don't hang around very long. They're very reactive intermediates, okay? And you see these types of intermediates form often, okay? And many of those have been proposed in a slew of different mechanisms in organic chemistry. The sequence over here on the right-hand side is a little bit different, okay? What do you notice that's different about the right-hand side to the left-hand side? Because they're both trying to achieve this here, okay? What do you notice the difference between these two? Because the cleavage, if you look, the R group is the rest of the peptidoglycan, okay? So the cleavage is happening here. If we go back, you can see that right there. See it? So the R group is here. So, coming to here, what's the difference between these two?
The aspartic acid actually binds on the right side, whereas on the left it's just kind of hanging around.
Okay, so the aspartate residue, or the aspartic acid, I mean, it's in the anionic form, right? So that's why they're calling it the aspartate residue, is that it's covalently attached. So Megan's right. It actually does the attack as opposed to doing what? As opposed to just hanging out and stabilizing, right? So Withers and co-workers propose that it does not undergo electrostatic interactions, and the reason why they proposed this is they actually isolated the enzyme intermediate. The enzyme glycosyl intermediate was apparently stable enough for them to either detect or actually isolate and characterize that intermediate before moving on with the cleavage. So my questions to you today, number one, what was the rationale behind Phillips' proposal of the half-chair conformation of the NAM reaction site? And number two, is there literature precedence formation for the oxocarbonium intermediate? Number three, what tools were utilized to investigate the mechanism of this process? Can you find other examples not listed in your book for this particular process? What about solvent? How does solvent play a role in the mechanistic enzymes or insights of the catalysis? And number four, are there any articles that support the Phillips mechanism for electrostatic stabilization? So I want you to go through this. If you've not read it thoroughly in your book, I want you to take time, read through that, discuss it with your classmates. But I want you to answer these questions as a group, turn those in, and I will count them as points for you guys. Okay? All right. Get to it.
It works. It has the words on it. It has the words.